understanding the law of mass action is crucial for grasping how chemical reactions achieve equilibrium, where reactant and product concentrations stabilize in a dynamic exchange. The synthesis of ammonia exemplifies chemical equilibrium, with isotopic analysis revealing the equal rates of forward and reverse reactions, maintaining constant ammonia concentration over time. Isotope analysis demonstrates dynamic equilibrium, where continuous reactant product transformations occur, ensuring no net change in the overall composition of the reaction mixture. Equilibrium is attained irrespective of starting conditions, whether beginning with reactants or products, as reaction rates equalize, stabilizing concentrations over time. In the formation of hydrogen iodide, equilibrium is reached as reactant concentrations decrease and product concentration increases until they all stabilize. An equilibrium mixture comprises specific reactant and product concentrations that remain constant, crucial for optimizing industrial chemical synthesis conditions. The law of mass action, introduced by Goldberg and Vage, defines equilibrium concentrations through a mathematical relationship integral for understanding chemical reaction dynamics. Experimentally, hydrogen and iodine reactions at 731 K in sealed vessels confirm equilibrium principles, with initial and product moles demonstrating balanced chemical transformations. Varying initial conditions in forward and reverse reaction experiments reveal equilibrium attainment, evidenced by constant color intensity and reactant product balance. Experimental observations confirm a stoichiometric relationship where reactant moles equal half the product moles, underscoring equilibrium composition consistency. Initial attempts to establish equilibrium concentration relationships reveal inconsistencies, leading to refined expressions that accurately represent constant values across experiments. Equilibrium expressions incorporate stoichiometric coefficients, confirming their essential role in formulating accurate equilibrium constant equations for chemical reactions. Omitting ake in notation simplifies equilibrium constant expressions, assuming equilibrium concentrations, and underlines the convention of expressing them in mol L1. The law of chemical equilibrium describes the constant relationship between reactant and product concentrations at equilibrium, foundational to reaction analysis. General equilibrium constant expressions relate reactant product concentrations mathematically, encapsulating chemical reaction dynamics into a concise formula. In ammonia oxidation, the equilibrium constant expression quantifies reactant-product ratios, providing insights into reaction behavior under equilibrium conditions. Notational conventions simplify equilibrium constant expressions by ignoring phase symbols, focusing solely on equilibrium concentrations of reactants and products. The equilibrium constant for H2 and I2 reactions illustrates the balanced nature of chemical equilibria, where product and reactant concentrations maintain a specific ratio. For reverse reactions, equilibrium constants are inversely related to their forward reactions, illustrating the reversible nature of chemical equilibria. The inverse relationship between forward and reverse reaction equilibrium constants emphasizes equilibrium's bidirectional nature and the dynamic balance of chemical systems. Changing stoichiometric coefficients affects equilibrium constants, illustrating how reaction representation influences the mathematical depiction of chemical equilibria. A general rule states that multiplying stoichiometric coefficients alters equilibrium constants according to the exponentiation of initial constants, reflecting reaction adjustments. The reaction quotient, Q, offers a snapshot of reaction progress, comparing current concentrations to equilibrium constants, guiding direction towards equilibrium. Comparing Q and Kc reveals reaction progress, determining whether forward or reverse reactions will dominate to achieve equilibrium, critical for reaction management. Equilibrium constants predict reaction directions, calculate equilibrium concentrations, and optimize industrial processes, enhancing efficiency and yield in chemical manufacturing.